right, good morning, everyone. So we're starting our second day of the workshop with Professor Gerald Teschl from University of Vienna on the Kdv shock problem. And it's going to be a Blackboard talk, so particularly excited about that. Thank you.
Okay, so let me begin by thanking the organizers for inviting me. It's really a pleasure to be here in person. You know, we all know after 2 years of spending most of your time at home and also doing most of your teaching in front of a laptop, I'm really happy that I can stand in front of a blackboard again, and so decided to use this blackboard. Okay, as you can see, I'll want to talk a little bit about the Kdv shock problem. That's a problem I spent a significant amount of my past time on. And I should maybe starting that this is a joint project started more than 10 years ago together with Iryna Egorova, my long-standing friend from the Institute of Long Temperature Physics in Kharkiv, and also Zoya Gladka. Her student participated at some time, our friend Vladimir Kotler, also from the Institute for Low Temperature Physics in Kharkiv, Johanna Micha, former student from Vienna, who also participated in this workshop, and also by now former student Mateusz Piorkowski. Who is now at the University of Leuven. Okay, and so I'm going to talk about the Kdv equation. You all know the Kdv equation, but let's still put it here. And I'd like to look at some initial conditions which have a step-like structure. And that means my initial condition should look like this. At t is equal to 0. I have two asymptotics. It will be, so this is the x direction. It will be 0 at x goes to plus minus infinity and some negative constant, let's call the constant minus c squared, in the direction of minus infinity, and in between it can be more or less arbitrary. So it should start out here and can do whatever it wants here, and then again should go to 0 on the other side. Of course, there will be some technical restrictions on this initial condition, but I'm going to come to this later. So what I would like to understand here is what happens for large time, what is the structure or the asymptotics of the solutions for large time. And the answer was known since a long time. Basically, you can split the plane into the xt plane into 3 regions, so we have here x equals minus c 6c squared t, and somewhere here we have x is equal to 4c squared t. And maybe I should also draw my asymptotics here. Of course, to the left of this region here, you're close to our asymptotic constant, but there will be a small dispersive tail. So you will have some small oscillations here. And there's a dispersive tail here. Then in this middle region, you will have an elliptic shock wave developing. So that's just a modulated elliptic solution of the Kdv equation. So the oscillations here will get larger and larger. And then, so this is an elliptic shock wave. And then on this region on the right here, you will just have some solitones traveling to the right. So this is the solitone region. And this is, you can easily verify numerically. In the old days, this was, of course, some challenge to do this numerically, but nowadays you just can fire up your favorite software, Maple or Mathematica, and solve, take some initial condition and then just solve it and then plot the corresponding solution. Okay, so maybe a few words about the history. So basically understanding this and kind of getting this picture here plus some formulas was done by Gurevich and Pitajewski. And that was in 73 and another paper in 74. They were using this Witham method and deriving this corresponding picture here on a physical level of rigor. And what I should also mention here is that if you go towards the soliton region, then this elliptic wave here is modulated. So these peaks here are just separating from each other. And eventually, when they have separated sufficiently far, will just turn into solitons. Okay, so they will just kind of disconnect from the wave here and become solitons, which move into this direction. And this was something which was first observed by Kruslov. And I think this was in 76, yeah. And this was quite a surprise because originally people thought that solitons are always connected with the discrete spectrum with eigenvalues, but here it's the leading ones are connected with eigenvalues, but there will be some which separate from this shock wave right here and were called asymptotic solitons and are not connected with a discrete spectrum. And I guess I should also mention here that a very similar problem, or we will see basically the same, almost the same problem eventually realizes if you look at what is called a soliton gas. So people were looking at the case where solitons are very close together. And in some sense, you can think of this elliptic shock as just a kind of continuous solitons. And in this case, yeah, this could be kind of thought of as some dense solitons, and they get less dense in this direction and then eventually separate. And you see this here. So what I'm saying here is also closely connected to this soliton gas problem, which was considered recently by Grava and Ken McLaughlin. Okay, and probably also was discussed already here in this workshop. Okay, so that's the picture here. There was also some work in the 80s by Novoshenkov, Bikbayev, and Shapirov. And maybe that's when basically there was then a long gap and nothing much happened here. And in, what was this, 2014, Leach and Needham also derived this asymptotics using techniques which are called matching asymptotics. And this was also around the time when we started looking at that problem right here. And I should really emphasize that except for Kruslov, these results were basically on a physical level of rigor. I mean, they were like matching asymptotics. You need to have an ansatz for the solution with some parameters, and then you determine the parameters. Of course, if you don't prove that the solution has the form of the ansatz, then this is not completely rigorous. And actually, this was similar for all these asymptotic problems for these equations until the work of this Riemann-Hilbert approach, until this was developed, which no longer did require an ansatz. And this is also the approach we're going to use. Maybe I should briefly mention, I don't want to say too much, or maybe I'll say something about this a little bit later. Let's move on and let's kind of try to set the stage on how to prove this results here. And the first thing I should say something about is, of course, the Cauchy problem. We should make sure that we're not talking about properties of the empty set. So before talking about asymptotics, we should make sure that we have a solution at all. And again, the Cauchy problem has a long history. And the first results are due to Thomas Capella. In 86. So at that time, people already had developed a scattering theory for the underlying Schrödinger operator with a decaying potential. And of course, this was also mentioned here in this workshop several times. This insight by Gardner, Green, Khrushchev, and Miura showed that the KdV can be solved using this inverse scattering transform. And people also already before that looked at the situation where you just have such a step-like potential and also developed scattering theory. So basically Cohen and Capella first looked at this step-like situation. And then of course it's also natural that you apply this to the Kdv equation and then use this to solve the Kdv equation. And Thomas Capella did this. And what he needed were, of course, some decay assumptions with respect to both sides. So on the left side, he basically needed a first moment for the perturbation. So you subtract your asymptotic constant and then you multiply by x and it should still be integrable. So this is the typical first moment condition. And on the other side, he required a little bit more. So, and there should be, minus, okay. And he needed at least a third moment for his condition to work, for this inverse scattering approach to work. And then again, nothing much happened for a very long time. Maybe I mentioned briefly, even though that's not so important in this context, it was not even known whether if you start with a Schwarz type initial condition, whether this will stay Schwarz type for all time. Together with Iryna Egorova and my student Katrin Grunert, we settled this case in 2009. Actually, we were looking at a more complicated problem where the background could be a finite gap solution and in fact different finite gap solution on both sides. So we looked at this situation basically for arbitrary moments. I don't remember what the minimal moment was for which this approach worked, but in particular, you would get Schwarz type in initial conditions. And then much later, Brodsky and Rybkin revisited this problem in 2020 and proved a technically quite impressive result. They were exploiting the fact that if you're doing inverse scattering, then one of the problems is, of course, always you have a left problem and you have a right problem, and you reconstruct two potentials, one from the left-hand side and one from the right-hand side. And you need to make sure that they agree if you do the full inverse scattering approach. If you just want a solution of the Kdv equation, you do not need this matching, and hence a one-sided approach suffices. And that means you can go technically with much less assumptions. And so actually they could do the same thing just for n larger than 5/2. And on the other side, they basically almost need nothing. They just need a small boundedness assumption, kind of local L1 assumption on the negative part. So the sup, when you integrate over some interval of the length of I of the negative part, then this needs to be bounded. So this needs to be finite. Okay, so that's this is probably technically very close to what you can do using this inverse scattering approach. And even more recently, there were some works by Ran Kilip and Monica Vijan, who looked at the Kdv equation. Of course, again, then this has a extremely long tradition, because the inverse scattering transform in some sense is not optimal from a technical point of view, because these moment conditions here, which are natural in the scattering theory, are not natural for the Kdv equation. So it's not clear that they are preserved under the Kdv flow. And typically what happens is that you throw in a certain amount of moments for your initial condition, and then you get out less on the other side for the solution. So this is not a natural condition for the Kdv equation, for solving the Kdv equation. Much more natural are L2 conditions. Why? Because you have these conserved quantities, and once you have the conserved quantities, then you know these are the natural objects. And of course, again, this was done for Kdv, an enormous history going down to originally until L2, and very recently by Kilip and Vijan using this technique trace formulas and conserved quantities, they were able to go down to H-1, which is considered to be the optimal result. And recently their student Lawrence uploaded a paper to the archive in 22, where he was able to handle initial conditions of such a step-like situation. So he basically just takes step-like function, it doesn't really matter, take something like this, something smooth, and was able to add a H-1 perturbation and then prove well-postness for the Cauchy problem. And clearly this can be considered the optimal result. Okay, so from that point of view, the Cauchy problem is totally settled, and I don't think you can say much more about it. The only thing is that all these results are, of course, technically very challenging, but in some sense, they are not good enough for us, because if you want to understand the long-time asymptotics, you need very fine control over the scattering data. So, and these results here don't give you this control over the scattering data, which we need for our approach. So we also have a corresponding theorem where we essentially set down and then refined what we have done over the years. And I'm not even sure whether I should put it down as a theorem. Yeah. Yeah, you take such an initial condition and then you remain in this space. And also, if I remember correctly, I haven't looked at the paper closely yet, but he also proves well-postness. But of course, then you also always have to discuss, things are getting very tricky here. In what sense is this a solution of the Kdv equation, right? I mean, how do you interpret the Kdv equation in this setting? So there are a lot of technical issues arising here. And of course, if I want to prove a picture like this here, the minimum, I need a classical solution, right? I want a continuous functions which has derivatives and so on and so on. And these results, as I said, don't give me enough control over the solution and over the scattering data over time in order to prove long-time asymptotics. And actually, you will see from the result, even for our case, we're not even looking at finite moments. We're even looking at some exponential decay to this asymptotics, because we want our scattering data to have an analytic continuation to a neighborhood of the spectrum. There are some technical ways of overcoming these kind of things, but all things are already technically quite complicated. And so we didn't want to go this extra mile, even though there are no principal objections to handling finite moments. But also for me, I really wanted to understand this asymptotics, and I'm not so much interested in having a technically optimal result, even though, of course, that would be important. But yeah, we spent more than 10 years proving what we have right now. So let's be modest, but there's clearly room for improvements in various ways. Yeah.
Existence, uniqueness, and
yeah.
independent.
Yeah. Typically, yes. And as I said, especially with well-postness, then it depends a little bit on what you understand by well-postnet and in your class. And here I think you get this out of the approach, because this is somehow the way how it is proven. I mean, you know existence for certain nice things, and then you just prove some continuity within your class. Okay, maybe I think I'm not going to write even down this theorem, because we're not going to need it, but it's of this style right here. We assume a certain number of moments which should be finite for the initial condition, both for the function and for some of its derivatives. And then we get out a classical solution, and both the solution and its derivatives loses some of the moments during the time evolution, or at least we can only prove that it has less than with what we have started with. But I think there is no point in really writing this on the blackboard. Okay, so let's continue. With setting up the problem. I guess this or you're probably all aware of this. The equation is solved using the inverse scattering transform. So we have an underlying Schrödinger operator, one-dimensional Schrödinger operator, where Q is the potential. The time is considered as a parameter, and we compute the scattering data for the initial time. The time evolution of the scattering data is linear and can be written down explicitly. This is the integrability of the Kdv equation, and then we do inverse scattering in order to compute the solution. So let me first recall a few things about here. So the underlying Schrödinger operator is just this one-dimensional Schrödinger operator right here. And the Schrödinger operator is time dependent. Time is just considered as a parameter in this context right here. And under these assumptions here, the spectrum of the Schrödinger operator looks like this. So you have a finite number of eigenvalues below the spectrum. The infimum of the essential spectrum is minus c squared. First, there is some spectrum of multiplicity 1 up to 0, and then from 0 on, you will have a spectrum of multiplicity 2 right here. So here you will have scattering theory with a reflection coefficient, but here, of course, the electron is not doesn't have sufficient energy to penetrate this wall right here. So if I start from this side, I cannot go to the other side. So that means everything is reflected, and I have no transmission right here, and hence I also just have spectrum of multiplicity 1. And what you can already see here from the spectrum, maybe that's something one should point out here, the spectrum is really what you see here, right? The solitones corresponding to the eigenvalues, this elliptic region here corresponding to the spectrum of multiplicity 1, and this dispersive tail here corresponding to the spectrum of multiplicity 2. And this is what you get in all the problems. So the asymptotics are just kind of a picture of the spectrum of your underlying operator. And also maybe that ties in nicely with this soliton gas remark, because from a spectral point of view, in some sense, spectrum of multiplicity 1 is very similar to eigenvalues. Okay, so this could also be understood in this way. Okay, so yeah. That's the operator. When you do spectral scattering theory, you define these Yost solutions. So you look at solutions of the underlying spectral problem, where lambda corresponds to the energy, but is now just taking as some complex number. And it's convenient if you solve this equation, of course, to introduce this parameter k, where you just take the square root of lambda. And depending on which side you're doing this, here 0 is your reference value, and here minus c squared is your reference value. So there are two natural parameters in this way. This setting here, k and k1, which are these square roots here. And we know that there are corresponding solutions, and these are the Yost solutions, which are just asymptotically normalized by just looking at asymptotically just look like the free solutions. One as x goes to plus infinity. On the other side, I'm going to call this phi1 here. As x going to the other side. Okay, so these are the corresponding Yost solutions. And then you start playing with these solutions. When you're on the spectrum, they will be complex valued. You have an operator of order 2. So that means you have two linearly independent solutions. Now we have two solutions. In the case where they're complex valued, if we take complex conjugated, we have 4 solutions. That's a little bit too much. There must be some linear relations between these solutions on the spectrum. And these are precisely the scattering relations. And when you write this down, you get transmission and reflection coefficients. You can do this from both sides, and these are going to be your scattering data. Also, you have your eigenvalues. So I'm calling them minus kappa j squared. And for each eigenvalue, there is a corresponding so-called norming constant. If you plug in an eigenvalue here, then this will be the corresponding eigensolution, and the inverse of the square of the L2 norm of this function here is this norming constant right here. Okay, and these are the scattering data, and the inverse scattering problem would be to determine the potential Q from this scattering data here. It turns out, of course, there are some connections between the scattering data. You will not need everything. You can write down a minimal set of scattering data. But I think I'm not going to say much about this. If you look at the transmission coefficient, then the transmission coefficient has an analytic continuation away from the spectrum. It will have poles at the eigenvalue, and it might also have some singularity at 0 here. This will not be a pole because it's not an eigenvalue, but if it has a 0 here, then it's called a resonance. Okay, and there are two possibilities. Either there's a resonance or there's no resonance. No resonance is the generic situation which you have most of the time. So having a resonance is something special. And it turns out when you look at the asymptotics, you will see this in the asymptotics, because in the analysis that makes a difference. But I'm just mentioning this, and I don't want to say more about this right here. And the resonance, of course, it's at the boundary of the spectrum at minus c squared here. Okay, yeah. So let me now put down this picture for the inverse scattering transform, just to be able to discuss this. We start with the initial condition. We compute the scattering data of the initial condition. There is a linear time evolution, so we can compute the scattering data at time t, and then we do the inverse scattering in order to compute the solution at time t. And this is the well-known inverse scattering transform. Okay, and then we have solved this, which is also known as nonlinear Fourier transform because it very much looks like the Fourier transform. Okay. Now, there are several ways, or in some sense, one can say two ways of doing this inverse scattering. One way is the classical way equation, which is this Gelfand-Levitan-Marchenko equation, and that's the classical approach of doing the inverse scattering. But it turned out when people were looking at the long-time asymptotics, this didn't really work very well. So people were not able to extract the long-time asymptotics out of the Gelfand-Levitan-Marchenko equation. Well, that's not quite true because there is one region, namely the soliton region, where this works. Okay, so the asymptotics in the soliton regions can be done using the Gelfand-Levitan-Marchenko equation. Actually, this was what Kruslov was using, and this is the reason why he could do everything rigorously. But for this dispersive tail here, I don't know a way of getting this out of the Gelfand-Levitan-Marchenko equation, even though I would be very much interested in doing this, and that also Ira would be extremely interested in seeing this done. But it seems nobody really knows how to do this rigorously. And for this reason, this Riemann-Hilbert problem approach was developed, which kind of overcomes this problem and which works in all three reasons. Just very few words. Originally, it was proposed by Manakov for the Kdv equation. So he said that might be a way of doing it, but again, he couldn't really do it. He just pointed out there's this Riemann, you can formulate the inverse problem as a Riemann-Hilbert problem. And you probably can do the long-time asymptotics using this. And again, formally, you can easily see the solitones and some hand-waving arguments why the rest should be decaying, but you won't get more out of this. And the main reason is if you look at this Riemann-Hilbert problem, then you have some oscillating terms. And in order to understand the contributions, there is an underlying model problem, and you need to solve this model problem. And Manakov had no idea how to solve this model problem. And then Itz came, and he saw some work from Chinese people working on these Riemann-Hilbert problems. And he realized that that could be used also here. And he was able to show how to solve the underlying model problem and at least formally write down the asymptotics without using any ansatz, just using this Riemann-Hilbert problem, even though his arguments, of course, still were to a certain extent hand-waving. In particular, what is always very difficult in this connection in proving that the real solution is really asymptotically given by the solution of the model problem. So he just showed how to solve the model problem. And this was then done later in the seminal work by Daift and Zhao, where they developed a full-fledged method of proving that the solution of the model problem really coincides with the asymptotics of the solution one is interested in. Okay, and so this is our weapon of choice here for attacking this problem. And I would like to explain a little bit about this next. For simplicity, I'm only going to look at the elliptic shock region. The dispersive region here is very similar to the classical case where you have decaying solutions. So this is well understood, and also the soliton region is similar to the classical case where you have a decaying potential and is well understood. If you're interested in this here, there's a review paper which I wrote with Katrin Grunert some time ago, explaining this method for Kdv with decaying. So that my decaying potential initial condition, that might be a starting point if you want to know more about this here. And also we played in the soliton region, both with these approaches, and we're trying to kind of get optimal results out of these approaches. And you can find the corresponding papers on the archive. But I guess Ira already talked about this here, so I'm not going to go into this at here. Okay, so we only look at the shock region. So the first thing, most of you probably know what a Riemann-Hilbert problem is, but let me just give you a brief reminder for those who are not so familiar with this. Now, the idea is the following thing. You write down a vector-valued function, I'll call it M, depending on 3 parameters, K, which is just our energy parameter right here, and X and T. I'm really looking at this as a function of this parameter K here, because it's going to be holomorphic away from the spectrum. Okay, so how does the spectrum look like? We took the square root, so we have a holomorphic or conformer mapping right here, which will unfold the complex plane. So it will be the full complex plane. The real line here will correspond to the spectrum of multiplicity 2. Here, there will be 2 intervals from IC to minus IC, corresponding to the spectrum of multiplicity 1, plus there will be the eigenvalues here. Everything here, of course, is symmetric. Plus, there will be the corresponding eigenvalues. And the thing is that if I look at these Yost solutions, then, of course, since the equation is analytic with respect to K, also the Yost solutions are going to be analytic with respect to K away from the spectrum. So they will be analytic functions in this plane right here, but they will not be have an analytic continuation towards the spectrum. Okay? Towards the spectrum, you will have continuous limits, but the limits will be different from different sides. Because in some sense, the different limits from the different sides correspond to the function and the complex conjugate function. So as I mentioned before, these functions can be connected using the scattering relations. These are these coefficients, transmission and reflection coefficients here. So that means if I come from this side and if I come from this side, I can connect. There's a linear connection between these limits, a jump condition, and this is precisely what the Riemann-Hilbert problem is, right? I'm looking at the sectionally analytic functions, which is non-analytic away on some curve, but I have limits from different sides which satisfy a linear relation. So there's a linear map mapping the limits from one side to the other side, okay? And the Riemann-Hilbert problem is, knowing these linear relations, find the corresponding function, okay? Of course, the solution is not going to be unique the way it is set down here. Why? Because if I multiply by an entire function, I'm not going to change any limits. So I also need a normalization condition at infinity. So typically you require this to be 1 at infinity to get a unique solution of this problem. Okay, so what is one doing here? The idea is the following. I'm just using 2 definitions on the upper half plane and on the lower half plane. I'm defining a vector, and this vector basically consists of the 2 Yost functions. Okay, so a vector, first component of the vector, second component of the vector, first Yost function, second Yost function. Why do I multiply these things here? Well, I have, where is it? Somewhere up there. I have these asymptotics. So as k goes to infinity, I would have an essential singularity. I don't want this essential singularity, so I'll just multiply with these factors. for them to go away such that I can normalize at infinity. Otherwise, essential singularity, there's no way to normalizing this. So I need to take this away. So this will be 1 at infinity. I'm also adding the transmission coefficient here, but in some sense, that's just for making all the formulas nicer, if you want. Okay, that's not crucial. And on the other side, I'm making everything kind of symmetric. So I'm just exchanging the 2 components here. Okay, sigma 1 is, this Pauli matrix. But this just means I just exchange these 2 components here, and I'll take the same thing. So this is on the upper half plane kind of, okay, in C plus, removing the spectrum, and this would be for K in the lower half plane, C minus, again, removing the spectrum. Okay, so this is the function here. And when I write this down, what I get is this so-called Riemann-Hilbert problem, which is solved by this thing here. So the ingredients here is, of course, the most important one. I already explained this, will be the jump condition. Okay, so this is typically written in this way, and I'm not writing x and t because x and t are just going to be some parameters in these problems. They're always present, but I'm not saying much about this here. So plus and minus in this context really means plus is the limit from above, and minus is the limit from below. And there is some matrix V of k, which can be written down explicitly containing these scattering coefficients right here. And this is the connection. And that's the jump condition, which is the most important one. Then there will be pole conditions because I do not only have these jumps, I also have the eigenvalues here corresponding to first order poles. But in this case, because of this transmission coefficient, only this first component here will have poles, right? The other one will have no poles, but at an eigenvalue, the 2 Yost functions must agree because both of them are square integrable and there is the eigenvalues are simple, so they must agree, and this is the pole condition. Okay, saying there is a linear constant connecting these 2 functions at an eigenvalue. And because of the first order pole here, this function will show up at the residue. And so it means the residue of the first component is a multiple of the value of the second component. This is the pole condition here, which is important. The pole condition can be rewritten in a jump condition by taking a little circle around the pole, removing the pole inside and creating a jump on this circle here. So in some sense, these 2 things eventually can be easily combined so that you just have a jump condition and don't have to worry about this pole condition. Then in order to get uniqueness, you need a normalization condition. Because otherwise you multiply with an entire function and your jump condition is not going to change. And it basically says you normalize it to be 1 at infinity. So both components should be 1 as k goes to infinity. You need to worry a little bit about how this is done because you're not analytic here. But let's say you go to infinity away from the spectrum. Let's take something like in this direction, whatever you want. It doesn't really play a role, and you could even handle going along the spectrum because things are continuous. But let's not worry about this. Essentially, you want such a normalization. And that's not so obvious. I also require a symmetry condition, namely this symmetry condition here. If I replace k by minus k, it corresponds to exchanging the components right here. Of course, for our problem, this is kind of by construction, okay? This is precisely how I constructed the solution. And at this point, it's not so clear why this is important, but yeah, okay. So let's stop for a second here. So we have this Riemann-Hilbert problem, and the thing is, given V, find the corresponding solution of this Riemann-Hilbert problem. Once you have the solution, Q can be easily, there's a simple formula for this, reconstructed from the solution. And what you want to do is you want to solve or write down the solution asymptotically. So the idea is the following. If you look at this jump matrix here, as I said, the time evolution for the inverse scattering here is linear, okay? So the coefficients are going to look something like reflection coefficient at time 0, e to the t something, okay? And that's really like these oscillatory integrals, because e to the t something, your phase function is going to be purely imaginary. So this is going to oscillate faster and faster as t goes to infinity, okay? And the idea is, of course, you can throw away these terms. And that's already non-obvious in case of an integral, and even less obvious in case of such a Riemann-Hilbert problem. And the way of showing this, and this was really Dive and Zhao pointing this out, is you can make contour deformations, right? So for an integral, one way of proving this decay in case of oscillations is you say if everything is analytic, okay, let's move the path of integration into the complex plane, into a region where it's exponentially decaying, and then you can throw it away. The same idea here, you move your contour into the complex plane such that these terms are decaying, and then you can throw them away. Now, problem here, things are more complicated. You have a matrix, and you will have e to the plus and e to the minus into your matrix. So if you move into the complex plane, one will decay, but the other one will explode. So what you need to do is you need to factorize your matrix into these two components and then move these components into different regions of the complex plane. Problem, matrix multiplication is not commutative. So you can move it this way, but you cannot move it the other way. Okay, and that makes things very, very complicated. And in this region here, in some sense, it works out nicely. You can move easily the factors into the right ways, but here that doesn't really work. So here things get really, really complicated. And what you need to do is you need to replace your phase function by another phase function. And that's difficult to find. But once you found this, then again, you can factorize and move things into the complex plane and throw away most of your factors, most of your contours. And what is left over is this model problem. And then you need to solve the model problem in order to get the solution. And of course, you also need to prove that the solution is close to the model problem, because that's similar to the classical method, right? When you move into the complex plane, you have the stationary phase points where the situation changes. And you need to go through the original contour to the real line at the stationary phase points. This will give you a contribution. And again, you will have to compute these contributions in order to show this. Okay, but I don't have much time left. So let me make a few remarks and then try to show how I think the model problem should be solved, because this was the main point, was intended as the main point of my talk here. So the first thing I wanted to point out is the issue matrix versus vector Riemann-Hilbert problem. In this business, most people prefer to work with matrix Riemann-Hilbert problems, meaning I'm looking for a matrix satisfying this jump condition. One of the main reasons is because if you look at the matrix problem, uniqueness already comes for free. Why does it come for free? Because one can easily check in our situation, the jump matrix will have determinant 1. And when you have a jump matrix with determinant 1, the solution is unique. Why? Because if you have two matrices satisfying these conditions, you take one matrix, multiply with the inverse of the other matrix, make a little calculation, and you see that this product here has no jump because the jump is going to cancel. So that's an entire function. It's 1 at infinity. Liouville tells you that this is a constant, and that's basically it. Okay, so you get easily uniqueness in this case. And also, when you look at existence, you can rewrite these problems in terms of singular integral equation using these Plemel formulas. And then you can use Fredholm theory. And so once you have uniqueness, you get existence for free from Fredholm theory and so on. So that's one of the reasons why people prefer to work with matrix problems. And the second reason is also if you have two solutions of different problems, again, you can play this trick, multiply the solution with the inverse of the other solution, then those parts where the jump is the same or close to each other will cancel. So you can play many tricks which are very useful in the analysis. So for this reason, most people prefer to work with matrix problems. And of course, here you could say, okay, let's look at the matrix problem. Just look at the corresponding matrix solution. And the problem here is twofold. The first of all is the way we have set it up, it's a vector, right? We just have a vector valued solution. In order to get a matrix, of course, we would need a second linearly independent solution if we want something with determinant 1. And there's no obvious way of writing down a second linearly independent solution here. Okay, so you don't get this out of the problem. And moreover, it turns out, and that took us quite some time to realize, you don't always have a second solution. Well, in some sense, you always have one, but it might be singular. Okay, and in all the previous problems we looked at, this did not happen. So we did not worry about this. And this was kind of the first problem where it suddenly happened. And you only need it in the end for the model problem, that the model problem does not have a matrix, a non-singular matrix valued solution. Okay, and this is the reason why, at least for KdV, we prefer to work with the vector solution. And here it's important to impose this symmetry condition, because the vector solution will not be unique without this symmetry. Because again, precisely, there are certain situations where there will be a second solution. You will have a vanishing solution of the corresponding vanishing problem, so you will not have existence. And of course, that also destroys your identity argument. You will not have a second non-singular solution. And this is the reason why we work with the vector problem. And you also need to work around this problem for the model case, where you just have this singular solution. Okay, but let me really emphasize this symmetry condition, because that also took me some time to figure this out. In particular, if you look at the literature originally, when I first was looking at KdV, people will just tell you, well, that the solution of this problem is unique, and just look at this book on Riemann-Hilbert problem and scattering theory by Dave Spiels. And I don't remember, you can find it there. And I was looking there and couldn't find it. And then eventually realized that even if you look at the one soliton problem, this happens. And even for the one soliton problem, there is a second solution without the symmetry condition. Okay, yeah. So I have 4 more minutes. Let's be really brief at the end. So once you make these deformations, what you get is the following. Model problem. So the jump on the real line can be moved away such that everything is exponentially decaying. You don't have to worry about this, but this jump here will remain. But that's the point. After this deformation, most of the jump will be gone, will be moved to the complex plane where it's decaying. And here the jumps are going to be constant. Okay, so on this interval here, it will be just exchanging the components plus adding some I. Again, here that follows from symmetry. It's the same, but with minus I. And on this interval here, you will have a diagonal jump. And it's minus I delta, where delta, of course, depends on x and t. So it's e to the some constant times x plus e to the some constant times t plus some additional constant. All of these constants can be explicitly computed, but let's not worry about it. And you should solve this problem right here. That's the model problem. And I was thinking with Mateusz about what's the best way of solving this. Okay, in some sense, it's known that such problems can be written down in terms of, or the solution can be written down in terms of Jacobi theta functions. But usually that requires a lot of playing and making some ansatz and then determining the constants until eventually you find the solution. And then, of course, in the paper, you will just cut this whole story short and write down, OK, this is the solution, check it. It's easy. So we were thinking about how to solve this and also how to see what are all the possible solutions, what can happen here. And the idea is the following. I can only briefly sketch this. The first thing is we're going to replace maybe there's some color here. I'm going to replace the I by 1. How do I do this? Well, that's not so difficult because that just means I need to multiply with a function which has a jump on these two intervals here, and the jump on this interval should be I. Okay, so the limit from here and the limit from here should just, the quotient should just be I. This is easy to find because scalar Riemann-Hilbert problems can be solved using this Plemel formula. Actually, you can easily guess the answer if you take a square root. That means along the branch cut, there will be a jump of -1. If you take a fourth order square root, then there will be a jump of I. So basically, you just take a fourth square root having the branch cuts at these points right here. You multiply, and you will replace this I here by 1. Now, once you have done this, you realize that this can be considered as a sheet exchange as before, right? I'm taking two copies of this slit plane here and glue them together. And this jump here basically tells me I'm changing when I'm coming here and going to the other side. If I just flip the function on the other side, I'm just moving from this plane here to the lower plane and back. So in some sense, if I take the two copies, I have a Riemann surface, and the solution, the vector solution here, will be a single function on this Riemann surface, and the two components will be just a function on the upper sheet and on the lower sheet. Okay, and this way I have effectively converted this vector or matrix Riemann-Hilbert problem. In this context, it doesn't make much of a difference, into a scalar Riemann-Hilbert problem on a Riemann surface with these two cuts here, which is just an elliptic surface. Okay, and now then the next step is not so difficult. The next step is, once you have the surface, you use the Abel map in order to map it into the corresponding Jacobi variety. And that means you look for a function on this Jacobi variety, which is just a complex plane mod lattice. And you have two periods. One is in the real line, which is just 1. And so the function needs to be periodic in this direction. And in the other direction, if you go into the tau direction, it's not going to be periodic because you still have this jump here. Okay, but you get this jump in the other direction. So that means what you're really looking at is a quasi-periodic function on this Riemann surface, which is, or elliptic function, which is periodic in one direction and has this quasi-periodicity in the other direction. Okay, and now the nice thing is, of course, once you do this, you know such a function is uniquely determined by its zeros and poles. Why? Because if you take the quotient of two functions, zeros and poles are going to cancel, and also this jump here is going to cancel, and that means it must be a constant. So it's determined by zeros and poles. Now we need a non-singular solution. So we know where the poles need to be, and also we know the symmetry. The symmetry translates so that your period is actually not 1, but 1/2. And then you see you can allow just for one pole, you know where it must be. It must be here, such that you get a non-singular solution in the end. And then you can easily write down that there's precisely one singular, one symmetric solution. If you drop your symmetry condition, you can also take an antisymmetric solution. You know every solution must be a linear combination of these two. You can write down your matrix solutions, and you can precisely understand where must be poles and why there is no non-singular solution. Yeah, but that's the idea. You're already standing here, so my time is over. Yeah, thanks a lot for your interest, and yeah. Thank you.
Thank you very much for a very nice talk. Any questions? Maybe a quick question before we get out of the photo. Anyone online? Gino, is there anyone online? No. I had a very quick clarification. So the way you're avoiding the ansatz in this last section of your talk is, so you're completely able to avoid the ansatz this way, right?
Yeah,
you don't have to do any guessing.
This whole method, you do not need an ansatz, because in the end, you always have a model problem and you need to solve this model problem, right? And apart from being able to using this abstract Fredholm theory in order to prove existence of such problems, as I said, you can write down the solution, but you don't need an ansatz, right? You can write the solution no matter how you got it, and then just verify that it is a solution. But you don't need an ansatz for the asymptotics, because all these ansatz-based things means you say, you suppose the solution is of this form, you have some unknown parameters, you plug this into your equation, you use the conservation laws, and then you get formulas for the parameter, in some cases even formulas for some of the parameters, but not for all of the parameters. So I also spent quite some time even for this dispersive tail here. There are a number of parameters in the asymptotic formulas, because it's known it should be the similarity solution of the Kdv equation, which appears here. Some of the constants, like the amplitude, you get out of energy conservation. So this can be done easily, but there's a phase shift. And this phase shift, I haven't seen anybody getting this out of the ansatz, what the precise phase shift is. So I'm not sure about it, but I think that using the Riemann-Hilbert approach really was the first time when this constant, this phase shift was determined. In the paper by Daift and Zhao, they are claiming this was done before in the Russian literature, but I checked the papers they referenced to and couldn't find it there. I also wrote to Percy, because there's a sign error in his paper, and this sign error cost me a lot of so I wrote to him where I can find it, and he couldn't remember. So probably it's somewhere hidden in the Russian literature, and people got this with this ansatz based, but I was not able to dig it down. Yeah, and that's the thing. And here you're solving problems, and once you have the solution, that's it. And maybe you do an ansatz to find the solution, but in the end you can verify it. Right. So from that point of view, there's nothing you need to know beforehand on the precise form of the asymptotics, even though probably it's always helpful. And I should also mention, I mean, when I started doing these things, it's extremely helpful to do numerics. I mean, even though I'm no numerical person and I'm not very good at these things, but it's very helpful when you know what you're supposed to prove before you start. And also for me, realizing that what you see in these problems is always the spectrum helped me a lot. And just then you start seeing what you need to do and what is going on here. So I should also emphasize, even though as I said, I'm no numerical person, but it's still important to do some numerics and to see what you can expect and what you should do, even though in the end the proof doesn't require it. It might be difficult in many situations to find the proof and to find the answer without having numerics and already know what you're looking for.
Very nice. Let's thank our speaker again.